Okay, the remaining time, I'm going to start with topic 28. Okay, and we'll hopefully make some progress as much as we can. So on Thursday, we'll have more Q&A time for your projects. Okay, so the last topic here is finally, we're able to talk about how to use regression to make inference. Okay, so remember the sequence, like we're ending with regression. We talked about why, like how regression works in the first place, right? And then we introduced the least square methods. And then from there, we just talked about the diagnostics of the regression just to make sure that it's good, okay? And then lastly, if you figure that, okay, it is good, then I do want to use my regression to make certain inference, and then this is the last topic, okay? And what we're doing here, as you can see, is that we're gonna talk about how to make prediction, okay? We can even come up with prediction confidence interval, okay? And we can also make inference about the slope, which is the, the value, like the slope parameter that we're able to estimate. And in this case, you will see that we put it into practice with a particular data set. But all of this, like I said, could be very relevant to what you're doing for your project if you're doing a regression analysis, okay? So make sure that if you do that for your project, you do cover about like how to come up with a linear regression in the first place, how to do diagnostics, and then lastly, how to do inference using the regression that you have come up with, okay? So I think for today, maybe we should be able to cover the first subtopic here is thinking about regression model. Okay, we've been talking about it, and then we told you how you can do the calculation to get the slope and the intercept. But we do want you to think a little bit more about what the regression line is really doing, and in some way, I guess, what it is not doing. Okay, so let me show you this slide first. Okay, let me just use here. Okay, yeah. So the model of linear regression, what it includes, as we were saying, is that, well, you have all of those data points, right? And what we're assuming is that, right, there is the best line, the least square lines, right, going through the cloud, the data cloud, okay? And it's minimizing all of this, like the sum of the square, okay? So that's what we mean by the least square, okay? And think about it, like what we're doing really is that we're going through this line, okay? And we are having what we know, right, of all of the residual, okay, that we are getting, right? Residual, again, is defined to be the observed value minus the fitted value, okay? So with 4 data points, okay, we're getting, well, 4 residuals, right? And then, like I said, the least square methods, the linear regression that we're doing is minimizing the sum of the square of the residuals, okay? And we know as part of the assumption, as well as because of that assumption, we do the diagnostics later as well, is that those distance or like those residual, they should be from a normal distribution with mean 0. Okay, so this is what I think a linear regression model really encompasses. Okay, so it's a lot of stuff, okay, even though it's kind of straightforward just to fit the line, but it does tell us a lot of stuff, okay? So what I want you to think is that here, okay, what we're saying, and you probably have heard about the term signal and noise a lot in machine learning or even just in standard like statistical methods in general, is that we're trying to capture the signal, which is the regression line, right? As well as in some case that trying to get rid of the noise as much as we can. But regardless, for a model that we're doing, you have the signal and the noise at the same time. Okay, so the signal in our case is the regression line that we're trying to fit, right? The noise is the residual, okay? So if I actually just tell you this 4 dots, okay, I'm only showing the 4 dots, okay? Earlier I was showing you, okay, yeah, we can be so sophisticated trying to fit a line going through it, but really whenever you're working on problems as a data scientist, what you get is this, right? You get 4 dots. Okay, and you're going to try your best to explain the variability, okay? And then we know that the method that we're talking about here is linear regression, okay? So I do want you to start to think that, well, the regression line that we're fitting, like how good it is, okay? And at the same time, what it is really doing, okay? So this demo, which will lead us to talk about the inference, okay? But I do want to show you this because I think it's pretty interesting. And maybe will encourage you, motivate you to think a little bit more about what exactly we're doing. Okay, so as usual, we have a lot of functions to load, nothing more than before. Okay, just so you know. Okay, we have the standard units, correlation, slope, intercept, fitted values and residuals, okay? All right, so I'm introducing a new function here, which I really want you to, I will explain it now, not line by line, but to a certain degree, and then I will encourage you to check it out in more detail later. What I'm doing here is that, suppose I create a function here that if you tell me the true slope, okay, of your, the slope that we're trying to solve, let's just say there is a true slope, okay, we know it's the truth, okay, and there's also the true intercept, okay, I give you those two values, okay, and I also give you the sample size, okay, and what we're doing with this function, as you can see, is that, first of all, we're going to simulate some x value, which is the predicted values from a normal distribution, okay, and then we also going to simulate the errors. Okay, remember the errors, the residuals in our linear regression model is what? They should follow a normal distribution center at the mean. Okay, so we are able to simulate the errors as well. So in some way, if we're able to get simulated x, the predictor, and then the simulated errors, if I use the true slope times my x plus the intercept, the true intercept, right? And then plus the error, I can get a new set of y. Okay. So what we're doing here, as you can see, is that we simulate x, we simulate y, okay, using the true slope and the true intercept, okay? And what we're trying to show you is that how the sample size is playing a role in terms of how good the linear model that we're able to fit, okay? So you will see that once I run this model with certain true slope and true intercept and sample size, we will see 4 different plots here, okay? Well, we'll have the true line, that is with the true slope and the true intercept, okay? And then also what we get to see without any lines, just the dots, okay? We also gonna show you, well, with x and y, we can fit a regression line, right? So we are able to fit a regression line. So I do a 3rd plot, and then we do a 4th plot of looking at how close the true line and the fitted regression line is. Okay, so the true line, as you know, is the truth, okay? The regression line is the best guess that we can get, okay, or the best estimate that we're able to get. So here, this function, like I said, I think is really interesting, is that it can tell you, well, in some cases, probably doesn't work really well, and then that might be something that we need to keep in mind, okay? So here I'm doing 2 demos, okay? In both cases, the true slope is 2, the true intercept is -5, okay? I'm just playing with the sample size. Like I said, what we're trying to, the variable here is how sample size is affecting how close the true line and the regression line is, okay? So let me show you the first one. Okay, so be prepared, let's see. So this is the true line, okay? And all of the dots are only 10 data points, okay? So the true line is going through like this, okay? And then so for us, if you are doing a regression, this is what you're gonna get, okay? You only get a data cloud, okay? And now the question, like I said, is that because with this 10 data points, we're able to fit a regression line, right? The regression line is like this, okay? Not exactly the same as before, right? As you can see, like the slope and everything might be a little bit off. If we put it together, we can see that, well, there is some pretty significant discrepancy here, right? Meaning that, well, if I get this 10 data points, I know I was told that the true intercept is 2, a true slope is 2, and then true intercept is -5. My regression line going to tell me something quite different, okay? So this, I just wanted to highlight, is not a drawback of linear regression, like the method itself, okay? The more important issue here is the sample size, okay? If the sample size is too small, you just have so many uncertainty going on, right? You don't have enough data to support in some case, and that's why we really highlight the importance of getting a large enough sample size, okay? So now if we try to do it on 100, I think we will rest assured that linear regression is fine, okay? So here, first of all, right, this is the true line, okay? There are a lot more data points going on, okay? And this is what you're gonna get, to see if you, just were given the data set. And then we fit the regression line, okay? It's the estimate of the true line, okay? And see how close they are here. Okay? So I'm sure if you're gonna try it out, and like I said, we don't have the chance to talk through like each line by line, but the general reasoning behind or general logic behind of this function is trying to use the true slope and true intercept and a given data sample size. We're trying to simulate the true line and then also do an estimate of the true line, which is the linear regression line, and see how close they are. Okay. Our goal here is to tell you that sample size plays a very important role. Okay. So in this case, I guess if it's, if anything, I guess related to any of your projects will be that if you are doing a linear regression or maybe any other thing that you're trying to do, make sure that you have a, well, random sample in the first place, right? But at the same time, make sure that the sample size is not too small, because as you can see, well, even if we know the truth, if you have a too small sample size, the estimate of the best line, or the estimate of the true line could be quite far away from the true line itself. Okay, so that could be worrisome. But like I said, if you have large enough sample size, you should be good. So don't worry too much. But we're trying to use this as an example to show you that when sample size is small, how badly the estimate could be. Okay. Yeah, so that's all I have for today.
Right. All right. Happy Thursday. So today is the last lecture we have today. So honestly, I feel a little bittersweet about that. I think it's good that the semester is coming to the end. I think we all deserve a break after the semester, after the semester we've gone through. But I'm sad. I'm sad that things are going to be ending. Just a little bit of logistics before we come in. We'll wrap up kind of our last topic, talking about using regression to do inference. And then Monica is going to come back and join us. We'll give you some time if you have any questions about final projects or any questions along those lines. As far as kind of the end of the semester logistics, today's our last lecture. We'll have our last lab on Friday, and your final projects are due Sunday night. And so again, kind of as always, if any of those deadlines if you're not feeling great about any of those deadlines, if you need a little bit of time, come chat with me and Monica, and we're happy to kind of accommodate kind of reasonable requests for that. And then we'll also leave some time at the end for you to work on to do your CEQs. Okay, so let's pick up where we left off last time. And so kind of as a quick review, as a quick review from where we were last time, we started talking about the regression line as a model. Okay, and so the way we've kind of looked at this is that we've had some data that we've collected from a population. We have those data points, and then we've calculated the regression line from those data points. And we've seen that if the relationship between those 2 points is linear, the regression line is going to be best. I'll put best in quotes, best in the sense that is going to minimize the root mean square error. That is the best line that you can draw through those data points. So that's kind of the interpretation that we've had so far. Another interpretation that we can have is the regression line as a model. And what do I mean by that is that this is an explanation for our data. And so we say that our data, the truth is this linear relationship, this slope and intercept. And that is the model for our data. And the data that we see in the real world, that data is noisy. And so if you think about the regression line as a model for generating data, it kind of looks something like this. We have the green line shown here. This is our truth. This is the actual model. This is what we believe the actual linear relationship between our data is. And to generate data, we basically will take this truth, this green line truth, and we'll generate data, which is going to be noisy data. And how do we generate that data? Is that we're going to take points on the line, on our line, and we're going to create points that have some random noise added to it. And this noise is special in the sense that we're going to draw it at random from a distribution with an average of 0. Okay, and so if we have this model, if we have this regression model, we can generate data from that, and take a look at kind of that property as well. And by the way, right, this is kind of this idea of thinking about this regression model. That is the signal, that is the truth. And the data that we see is the data plus the signal plus the noise. And by the way, right, what is this noise? This noise is the residuals. This noise is the residuals from our regression. And so in the real world, this is what we see, right? We don't actually get to see the line. We get to see the data points from there. And so let's quickly kind of take a look at that demo again, because we saw it last time. Let me just put that down here. And so inside here, we have all of our standard toolbox functions. And then we looked over last time this idea of this draw and compare. And what this function does is this allows us to pass in a line with a slope is the first argument and the y-intercept. And then it's going to generate, using that algorithm that we just talked about, we're going to take that slope, that line with the slope and the intercept as truth, and it's going to generate, and for this first example here, 10 data points along that line with the random noise generated at random with a mean 0. And we can actually compare the points to the truth. Okay, so here is the green line is the line, the truth that we generated these data points. This is what we get to see, right? We don't actually get to see what the underlying model is. That's the model that we're trying to infer from the data. And so if we have this data here, and then we do our regression, we calculate our regression line from there. And so that is our estimate. The blue line is our estimate of truth. And since we've generated this data from this, we know what the truth is, we can compare the two of them. And you can see with 10 data points that it comes close, but it is not the actual line itself, right? And if we run this again, we can get a different set of data points and the line will be a little different. But we can see if we run it with more points, if we run it with 100 points, so now you can kind of see, even just by looking at what we get to see, you can see definitely more of a trend. We have more data points. And so our estimate presumably is going to be better. And so here's our estimate. And then we compare the two of them and you can see that they are closer than in this case, but there is definitely still some difference here. There's definitely still some difference between our estimate and the ground truth. And then finally, if we try it even with even more points, then we're going to start to see kind of a pretty strong convergence here, right? You can see that pretty much with 1,000 points that we got for this example, the two lines are very, very similar. Any questions about kind of this model, this regression model before I move on? Okay. So now we've kind of laid this groundwork for this idea of our prediction is going to have some variability built into it, right? Because we're looking at data sampled from a population. We generate this, so then we generate this regression model, and then we generate our prediction. So one of the things we would like to know is how accurate, how confident we are in that prediction. What are the confidence intervals of that prediction? And another way of saying that, what is the variability of this prediction? And so we're going to look at techniques how we can do that. So if we have our regression line, we can make a regression prediction. So if the data come from a regression model and the sample is large, right? So this is kind of harking back all the way back from when we started talking about sampling, right? If the sample from the population is large, the regression line is going to be close to the true line. And we saw that in that demo, right? As we increase the sample size, our our prediction of what the true regression model was getting closer and closer to the true line. And so with that model, right, to do our prediction, and this is not new, right? We've been doing this for a while now. If we're given a new value of X, remember X is our predictor. So if we're given a value X, how do we predict what Y is? We're going to use the same technique that we've done before. We're going to find that point on the regression line, and then that is going to give us our prediction Y. And we can see this. So this is so this data here is our baby data set, and this is we're going to look at gestation days. So and compare that to our birth weight. And so if we get this cluster of points here. And so the longer the gestation, there definitely seems to be kind of some trend line here. And so, and this is going to be birth weight in ounces here. And so we like to see if we can predict, given how many gestation days, what the birth weight of the baby is going to be. And so one thing that kind of jumps out here is that most of the data kind of falls between 200 and I'd say about 340. And we have a couple of outliers here. We have a couple of outliers here so these were, babies that were premature. And so let's get rid of the outliers and let's just focus on the data set between 200 and 340. And that seems like most of the cases here. So if we just look at that, using the where clause, you take the scatter plot of that, you can see that our data, it's the same data, it's the same shape of the data, but because we got rid of some of the outliers, the data looks a little more spread out. Okay, and so we've drawn our best fit line through that data point as well, and you can see that there's probably it looks fairly likely that there is a linear relationship. The longer the gestation of the baby was, it looks like it definitely increased birth weight from there. Okay, so this is going to be our model. This is going to be our model, and so now we can write a function that will do our prediction for us. Okay, and so what we have here is fairly standard from similar structure to all of the other functions that we were looking at. We're going to take a table. And then we're going to take our X, our predictor, and our Y, and then we're going to pass in, right? So this is going to be the columns. The X and Y are going to be the columns for our predictor and our prediction. And then we're going to give a new X value, right? So this is a new value, something that hasn't been seen before. And we're going to predict. We're going to predict Y from this given X value. And so how do we do that? Well, we do that by computing the regression line by calculating the slope and the intercept. And those are the functions that we've defined up above. And we're simply just going to take our new value, multiply it by the slope, and add it to the intercept. And that's going to give us our prediction. So once we have this function, now we can make any prediction. And so looking at the function here, so we're giving the birth table, and then our predictor is gestation values, and we're going to try to predict the birth weight. And here we're going to predict what the birth weight is for 300 gestation days. Okay, and so we predict that if a baby is gestating for 300 days, its birth weight is going to be about 130.3 ounces. Okay. And so here we can take a look at this. We can take a look at this, and basically all what we're doing with our predictor is we're moving up to the line. We're moving up to the line, and I've shown that as the yellow, the line there, and we're seeing where that point intercepts the line, and that's going to be our predictor. Okay, and this is hopefully this is kind of review for us, right? This is kind of what we've been talking about for a while now. And so now the question is, the data that we have, right? That is you can think of this, all of these data, this data cloud is a sample from the population. And so how good is this prediction? Can we make some stronger statements about our confidence with that? And so the technique that we're going to do, is we're going to we're going to come back to our old friend, the bootstrap. If you remember the bootstrap, we're going to apply the exact same technique to our scatter plots. And this is actually kind of cool. This is kind of cool and kind of amazing. And it's really kind of based from the exact same premise that what we did before. So if you think about what we did in our original bootstrap is that we had we have the population, and the population is too big to sample. We don't know. We don't have the resources to sample to survey the entire population. So we take a sample. And if that sample is large enough, that's a representative of the population. And to get our confidence intervals, what did we do? We resampled our sample with replacement, right? The replacement is the key here, is that we're going to resample with replacement. That's going to give us a bunch of data, and then we can move forward with that. And that's exactly what we're going to do. That's exactly what we're going to do here. So we have, and if you think about it, right, what is the scatter plot that we have? The scatter plot that we have is a sample from a population. If that sample is large enough, it should be representative of the larger population. And so what we can do is we can actually bootstrap the scatter plot. And so what that means is we're going to basically resample our our table with replacement. So we're going to sample. If there was like 500 samples in our data set, we're going to resample with replacement 500 times, and that is going to give us a new scatter plot. It's going to give us a new scatter plot. And then with that new scatter plot, we can generate a new regression line. We can make a new prediction. And let me show you kind of what that looks like, right? And so again, using the same data set here, what we can do is we can resample. And so here's our table here. And so what we're doing here is I'm just setting up some things to do to show the plots of the scatter plots of the resample. But really what we're doing here is we're just calling the sample function on our table. And the default is to sample as many times as there were rows in the table and to do the sample with replacement, okay? So this line right here is the key. This is where we're doing the resampling. So we're taking however many samples we had in our original table, we're resampling them with replacement, and then we're creating the new table here. And if you can see, if you take a look at that, so this gives us a new scatter plot, and it has the same general overall shape as our original scatter plot. The one thing you might notice is it looks in some sense a little less dense, less dense than here. And that's because we're doing resampling with replacement. And so we might be picking the same data point multiple times. And so the graph looks a little less dense because it's, one of these points here, like say the point over here, that might have, got selected a couple of times. So it's still the same number of overall rows in our table. But it looks, when we look at the scatter plot, it looks a little less dense. But you can see it still has the same overall shape, but you can see each of the plots are slightly different from one another. And so now that we've bootstrapped, now we have as many scatter plots as we want. And what we're going to do is we're going to do the exact same technique that we did with the bootstrap earlier in the course. Now that we have a new scatter plot, what do? We can make a new prediction. We can make a new prediction because by creating the new regression line for our scatter, and then once we have our regression line, we can then make our prediction. And that's exactly what I'm doing here in this code here. And so it's the exact same thing. All we're doing is we're taking our table here. So I'm just doing it 4 times for our 4 samples. And then so here's our resample. And then here's our prediction at, right? It's the same function, but I'm passing in our resampled table. from there. And again, making the prediction at 3, and we're going to see, we're going to get slightly different answers each time for this. So our prediction will always be at 3, but we're going to get slightly different predictors. Okay. So that's kind of the underpinnings of what we're going to do, and hopefully you can kind of see where we're going to go next with this. So now that we have now we have a way of generating as many scatter plots that we want by resampling our original. So now we can make the predictions. So what are we going to do? We're going to do the exact same thing that we did before. We're going to run this. We're going to run this 100,000, 10,000 times, and we're going to accumulate our results. We're going to and then look at the histogram of our predictions. And that is going to give us a measure of our variability, which then will allow us to generate confidence intervals from our prediction. So that's kind of the big takeaway for today, is that the bootstrap technique works for scatter plots. We can resample our scatter plot, generate a new regression line, and then make predictions. we can look at the predictions and look at the histogram of the predictions, and then we can get a sense of our variability. So, like I said, we can repeat these steps, look at the histogram, and then, for example, if we wanted a 95% confidence interval, we'll take the middle of that histogram, and that is going to give us our confidence for our prediction. And let's put all of that together and see what that looks like. And so now all we're doing here is we're basically taking all the things that we talked about before, and we're just wrapping it up in this one function here. And this hopefully all looks familiar to us because it's the exact same technique. So what we're doing here is we're initializing, right? So our function is going to be taking in our table, our X and Y labels. Here is our new predictor, the value that we want to predict. And then this is just telling us how many times we're going to run our simulation. Okay, so we make our array. And all we're doing here is we're resampling, grabbing our prediction, and storing that in this array. So we're just building up our array of predictions. So in this case, we'll default run it 1,000 times. And then what we're going to do is once we have our array of predictions, we're just going to take the 2.5 and this 97.5 percentiles. That's going to be our left and right. The thing in the middle is our 95% confidence interval. And then all we have to do left is just display our results. Okay. And so now that we have our bootstrap predictor, which again, because we've written it in this generic way, can work with any table. So here we'll reload the births table, and then we'll look at gestation days versus birth weight. Okay, and so then this is again, so the value that we want to predict the birth weight with 300 gestation days. And so now, since we've run the simulator multiple times, we're getting a histogram. And I've shown the confidence interval for that in yellow down below, the 95% confidence interval. And so what we can say is so the mean of this is we predict 127.1 ounces. Oh, sorry. No. This is I'm showing the confidence interval here, right? So we predict that the birth weight will fall between 127.1 and 131.3. with confidence of 95%. So we suspect that the 95 out of 100 birth weights will fall within that range. And there I've shown the width as well. And so any questions about that? Right? This is kind of exciting. This is kind of exciting that we can do this. So now what have we done? What have we done? We have the ability now to make predictions. So if you give a new value of something that we haven't seen in the data set before, we can make a prediction using our regression model. and that's cool. Like that's progress. But what's really cool is that now we can now kind of have confidence intervals around our prediction, and we can now say with 95% probability, here's the range of our prediction. Okay, so now what we've done is we've quantified the variability of our prediction, and that's great, right? All right, any questions so far? So, so now we can have predictions. And so since y is correlated with x, the predicted values depend on the value of x, right? That makes sense. The width of the prediction, right? So what is the confidence interval? The range of our prediction also depends on x. Whoops, sorry. And what's interesting about this, because if we think about what we did, we generated new scatter plots, we generated new regression lines, and you can actually look at all of the different regression lines. And one of the interesting things about this is that all of the regression lines that we generate are going to go through the mean of our predictor. Okay, so we have all of these lines, and they're all going to go through the mean. And so typically, because of this, intervals that are further away from the mean of x, you're going to have a wider range. For predictions near the mean, you're going to have tighter bounds from that. And so that's just something to kind of be aware of. So the confidence, right, the prediction interval you're going to have actually varies on where x is. And so and it turns out that linear regression models, they tend to be better predictors at the mean or near the mean. They have a less range. And as you go further away from the mean, the greater variability you have in your predictions from there. Okay, so any questions so far? Okay. So we looked at variability of our predictions. We can actually do the same thing for the slope. We can actually kind of do some inference for the slope, and we can generate confidence intervals on how well did our regression capture what we believe is the true slope. And so again, we're gonna stay right from our playbook. We're gonna bootstrap the scatter plot. We're going to find the slope through our bootstrap and lather, rinse, repeat. Okay. We're going to draw histograms of all the generated slopes, just like we did with the prediction, right? But we're not just doing a prediction for a particular value. We're now actually generating histograms of all the generated slopes. And then we can take our middle 95% interval. And so this is going to give us our confidence that the slope is actually the true line. Okay. Let's take a look at that. Okay. So again, same tool, same playbook here. And so here, what we're taking a look now is the same data, but I've just plotted out the slope. Okay, so this is our slope that we've gotten here. And so now what we're going to do is so instead of bootstrapping predictions, we're going to bootstrap our slope, and the code is going to look extremely similar. The only thing is really just the function that we're going to accumulate here. Right, we're going to accumulate just like we did before. We're going to resample. We're going to resample our scatter plot with replacement. But the only thing different than what we saw last time is this function, right? And so what we had before was we made our prediction based on some value that we wanted to predict. Here, we're just returning the slope. We're just going to return the slope here, and we're going to accumulate an array of slopes. Once we have that, we can take our confidence intervals the exact same way by looking at the 2.5 and the 97.5. And then well, here, because we can look at the slope of the original as well, and then we can display everything. Okay. And so this is going to take a while to run. I'm going to run this 2,500 times. And so now we've generated a confidence interval for our slope. And so, right, we know in this case, right, if we have the data, this is the slope of our actual regression line that we got. But when we do the resampling, we get this range. We get this range from about 0.38 to 0.55. It's actually kind of a wide range there. So you may be asking yourself, well, why do we want to do this? Why do we want to do this? Well, we want to have some confidence. We want to have some confidence that, because remember, at the end of the day, we're just kind of cranking through these numbers and it's going to generate something. And so we observed a slope based on our sample points, right? And so if we have a bunch of sample points, we'll always get a slope. You know, the algorithm is just going to kind of crank through and it will always give us a slope. But what does that slope really mean, right? Is it possible if the scatter plot just got that slope by chance, right? This is the eternal question that we ask when we ever have a sample. Was that value that we got from the sample, was that due to some underlying model, or was it due just by chance? So what do we do? And what happens if the line is actually flat? Okay. So let's take a look at, so this is just our draw and compare before. Okay, so this is the function that we had from last time, where we can give a slope, a y-intercept, and then a number of points. Okay, so now same function, but now what did I do? Notice I put in a slope of 0. Okay, so this, you remember, right? This is our regression. This is saying that there actually is no relationship. There is no relationship. So X has no predictive value. But notice, right, we can, even with slope 0, here's our true line, and it's shown at 10 because this is our intercept, right? So, and so remember, what do we see? We see this, right? We don't see this true line. We see this from there. And if we go through, when we run our estimate, we generate our regression, notice we actually get something that's flat. We get something that's flat, but it's not 0. It's not 0. If you compare it to the true line, which is 0, here, we actually do get something. And so we may want to ask ourselves, right, because if the slope is really 0, then you know, anything we see is really due to chance. And so how can we test or see if there's a slope? Well, we can do the exact same thing that we did before. We can basically set up the null hypothesis. Okay, our null hypothesis is that the slope is 0. The slope of the true line is 0. And so if this is true, if our hypothesis is true, that means whatever slope we see is going to be due to chance. Okay, and then of course the alternative is that the slope of the line is not 0. Okay, so let's look at actually another piece of data. Let's look at another piece of data from the same data set. But here we're going to look at the births, but we're going to compare the birth weight. We're going to try to predict the birth weight, but this time, instead of using the number of days, the gestation days, here we're going to use the age of the mother, the maternal age. Okay, and so if we go and just compute that slope, we can compute that slope. We see that it's small. It's actually small, but there is a slope here, right? There is this slope here, and if we look at if we look at this, you know, there is the average looks like a little under 120, but there is definitely some small slope. So the question we want to ask ourselves, is this a real effect, albeit small, but real? Or could this slope be due entirely to chance? And so hopefully now you can see why we talked about this idea of generating a histogram of the slopes, because we have a null hypothesis. We have a way of generating histograms by resampling, so we can generate a histogram of the different slopes. So what we're going to do here is the same thing that we did when we tested the null hypothesis back with our data, with like the mean or some other summary statistic. We're going to run the regression, and we're going to see if the slope of 0 falls within our confidence interval. If 0 falls within our like say 95 or 99% confidence interval, well then we cannot reject the null hypothesis. So let's do that with our data here. And so here we're going to run the bootstrap slope, and and it takes time, right? Because we're going to do it 2,500 times. And so here now we've generated, so remember, this is what we got from our data, 0.08, small but not 0. And here now we generated the confidence interval for our slopes. And we can see that 95% of the times it's going to fall from negative 0.1 to roughly 2.7. And we can see this down here. Now, the important thing about all of this is, where does 0 lie? 0 lies well within the confidence interval. So what that means for us is that we cannot reject the null hypothesis. The slope that we've seen here, this 0.08, could very well be due entirely to chance from there. Okay, and so that's why we want to look at the confidence interval of the slope from there. Okay, so wrapping up. This is basically just saying what we just looked at in the demo. Our null hypothesis is the slope is 0. The slope is 0. There's no predictive ability. The slope is 0. Alternative is, no, it's not. What do? We test. We bootstrap the confidence interval for the true slope and how do we do that? By resampling our scatter plot, 100, 1,000, 10,000 times. Look at the confidence interval. If it doesn't contain 0, then we can safely reject the null hypothesis. Otherwise, we can't. All right, this is kind of exciting. We have made it to the end, but don't run away. Don't run away. I know when I say we make it to the end, you all run away. Let me bring back Monica, and she'll join us. All right, Monica should be joining us shortly. So while we're waiting for Monica, any questions? I can stop the recording here.